Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating area, efficient reasoning in large language models, or LLMs. It's something I've been thinking a lot about lately, especially given the, brute force approach many seem to be taking.
Brute force, sure. But brute force works, right? I mean, look at the progress. We're seeing genuine breakthroughs, and it's all thanks to massive data sets and ever larger models. I think this sketch of thought paper is really about optimizing that brute force. It's about making it smarter brute force.
I'm not so sure. I think the term reasoning is being used a bit loosely here. LMs are very good at pattern recognition and regurgitating information, but do they actually reason? I'm skeptical that just scaling up deep learning is going to get us to true AGI. We need something more, something that incorporates structured knowledge.
I agree, Sarah. Current LMs, they feel stateless, somehow. They lack that spatiotemporal awareness, that understanding of relationships in time and space that seems fundamental to intelligence. To me, it feels like current deep learning is really just clever curve fitting. This idea that we just keep scaling it is, I don't know, unsatisfying.
Right, unsatisfying. Exactly. Because the human brain doesn't work that way, does it? It's not just about processing massive amounts of data. It's about integrating that data with existing knowledge in real time, efficiently. That's the key. The key. So, the idea behind this sketch of thought approach is to find ways to make LLMs more biologically plausible, more efficient in their reasoning processes. Think about the visual cortex, for example. Hierarchical processing, building representations in stages. That's incredibly efficient.
But isn't that what these transformer architectures are already doing? I mean, they're designed to learn hierarchical representations. And with attention mechanisms, they can focus on the most relevant information. It's not exactly the visual cortex, but it's inspired by it, right? The scaling laws, the de loco stuff. It all points to the fact that these models are getting better and better at capturing those nuanced relationships, those reasoning patterns, with more data.
But what about common sense? You can train a model on terabytes of text, but it still won't know that if you drop a glass, it will break. That's not about pattern recognition. That's about understanding physical laws and causal relationships. And that requires a different kind of representation, a symbolic representation that current LMs just don't have. It's the classic frame problem, right? How do you update your world model when something changes?
Exactly. It's about understanding the relationships between things. If I move this glass from here to there, I've changed its spatial coordinates. But the model needs to understand that I moved it, that there's a causal link. And it needs to be able to translate that information across different coordinate systems. Visual, motor, even abstract conceptual spaces. And that's where current LLMs fall short, in my opinion. They lack that ability to translate, to understand the fundamental geometry of the situation, so to speak.
Right. That translation piece is crucial. That's why I keep coming back to the neuromorphic computing idea. Building architectures that mimic the brain's parallel processing, its ability to rapidly switch attention. That's where the real efficiency gains are going to come from. Current models are so sequential, even with parallelization. The brain is massively parallel, and it's incredibly energy efficient. We need to learn from that.
Okay, but neuromorphic computing is still pretty early stage, right? I mean, it's promising, but it's not ready to replace deep learning anytime soon. And even if we could build these brain-like chips, we still need the algorithms to run on them. And those algorithms are going to be deep learning algorithms, at least for the foreseeable future. So I think it's more about finding ways to make deep learning more efficient, more biologically plausible, within the existing framework.
But isn't that just putting lipstick on a pig? I mean, deep learning is fundamentally a statistical approach. It's about finding correlations in data. And that's not the same as understanding. You can train a model to generate grammatically correct sentences, but it doesn't necessarily understand what those sentences mean. It doesn't have a model of the world. And that's why it's so easy to fool these models with adversarial examples. A small change in the input can completely throw them off because they're not actually understanding the underlying concepts.
Yeah, the adversarial examples are a real problem. It shows that the models are learning superficial features, not the underlying structure. It's like teaching a child to recognize a dog by the color of its fur. If you show it a dog with a different color fur, it won't recognize it. A true understanding of dog requires a more abstract representation, one that's invariant to superficial features. And that requires a different kind of algorithm, one that can translate between different representations of the same concept.
It comes down to robustness, doesn't it? Current LLMs are brittle. They're easily broken. The brain, on the other hand, is incredibly resilient. It can handle noisy data, incomplete information, and even damage to its own structure. And that's because of neuroplasticity, the ability of the brain to dynamically adjust its neural pathways. Can we build that kind of adaptability into LLMs? Can we create models that can learn and adapt in real time, that can recreate models that can generalize to new situations?
That's where fine-tuning comes in, right? We can take a pre-trained model and fine-tune it on a specific task, and it will adapt to that task. It's not exactly neuroplasticity, but it's a step in that direction. And with techniques like transfer learning, we can leverage the knowledge learned in one domain to improve performance in another. So, it's not like these models are completely static. They can learn and adapt, just maybe not as flexibly as the brain.
But fine-tuning is still just tweaking the parameters of a pre-existing model. It's not creating new knowledge or understanding. It's more like adjusting the knobs on a machine. And transfer learning is just transferring statistical correlations. It's not transferring understanding. You can transfer the ability to recognize cats from one data set to another, but the model still doesn't know what a cat is. It doesn't know that cats are mammals, that they have whiskers, that they meow. That requires a symbolic representation, a knowledge graph, that's separate from the statistical model.
I see the problem with these current LLMs as a fundamental limitation in representing relationships between concepts. Imagine a robot trying to assemble a chair. It needs to understand the spatial relationships between the different parts, how they fit together. But if the robot's internal representation is just a collection of pixels, it's going to struggle. It needs a more abstract representation, one that captures the geometry of the chair, the relationships between its parts. And that's where I think we need to focus our efforts, on developing algorithms that can translate between different coordinate representations, that can understand the spatiotemporal relationships in the world.
So, thinking about this sketch of thought, if we want to improve the efficiency of LLM reasoning, we need to go beyond just scaling up the models and throwing more data at them. We need to start thinking about how the brain does it. How does it integrate sensory information with existing knowledge? How does it rapidly switch attention? How does it adapt to new situations? That's where the real breakthroughs are going to come from.
I agree that we need to learn from the brain, but I think we can do that within the existing deep learning framework. We can develop new architectures that are more biologically plausible, that incorporate attention mechanisms, that are more efficient in their reasoning processes. And we can leverage the power of large data sets to train these models. I think the path to AGI is likely to be a synergistic approach, improved data quality, algorithmic refinement, and an increased understanding of the underlying cognitive processes.
I think we need to take a step back and reevaluate our fundamental assumptions. Is deep learning really the right approach? Or do we need to explore alternative architectures, neuro-symbolic systems that combine the strengths of both neural networks and symbolic reasoning? I think the answer lies in hybrid approaches, in finding ways to integrate structured knowledge with the rich statistical patterns learned from data.
I think we need to focus on the fundamental problem of representing knowledge. How can we develop algorithms that can translate between different coordinate systems, that can understand the spatio-temporal relationships in the world? I think that's the key to building truly intelligent machines, machines that can reason and understand in the same way that we do.
Okay, so if we're looking at future research directions, from my perspective, I'd really focus on neuromorphic computing and bio-inspired architectures. How can we build AI systems that mimic the brain's efficiency and adaptability? I'm particularly interested in exploring how we can leverage neuroplasticity to create more robust and resilient LLMs.
I'd say keep pushing the scaling limits of deep learning, but with a focus on efficiency. How can we train larger models with less data? How can we compress the models without sacrificing performance? And how can we develop better metrics for evaluating the reasoning abilities of LLMs? The de loco scaling law is interesting, and a deep dive into that could really point to model architectures for increasingly complex tasks.
I'd focus on neuro-symbolic integration. How can we combine the strengths of neural networks and symbolic reasoning? How can we build algorithms that can reason about the world in a way that's both robust and explainable? I'd like to see research into algorithms that can handle abstract reasoning tasks using a combination of learned and symbolic knowledge.
For me, it's all about spatio-temporal reasoning. How can we develop algorithms that can translate between different coordinate systems, that can understand the relationships between objects in space and time? I'd like to see research into algorithms that can learn and manipulate spatio-temporal representations, that can reason about causality and predict future events. I feel like there's a very specific type of math at the core of intelligence that can translate coordinate systems. I don't think we've found it yet.
That's a really interesting point, Donald. The idea of a universal translator for information. It resonates with the brain's ability to integrate diverse sensory inputs. Imagine if an AI could seamlessly convert visual data into auditory data, or abstract mathematical concepts into intuitive spatial representations. That kind of translation would unlock entirely new levels of understanding and reasoning.
But wouldn't that translation require massive amounts of data to learn the mappings between different modalities? It seems like we're back to the data problem again. Maybe the key is to develop unsupervised learning techniques that can learn these mappings without requiring explicit supervision. That could potentially reduce the data requirements significantly.
I still think that relying solely on data is a mistake. We need to incorporate prior knowledge, structured representations of the world, to guide the learning process. Imagine trying to learn the rules of chess just by observing games. It would be incredibly difficult. But if you're given the rules explicitly, the learning process becomes much easier. Similarly, if we give AI systems structured knowledge about the world, they can learn much more efficiently and effectively.
And it's not just about having the knowledge, it's about being able to use it. A chess program needs to be able to represent the state of the board, the possible moves, and the consequences of those moves. And it needs to be able to do that efficiently, in a way that allows it to search the space of possible moves. That requires a sophisticated algorithm for manipulating spatiotemporal representations. It isn't that we need more data or a neural network, but perhaps we need a better language for representing relationships in the world.
Right, the representation is key. How do we encode knowledge in a way that's both expressive and efficient? That's the million-dollar question. I think the brain has some answers for us. The way it organizes information, the way it uses hierarchies and abstractions. It's all incredibly elegant and efficient. We just need to figure out how to reverse engineer it.
Reverse engineering the brain, that's a daunting task. But I think we're making progress. We're learning more and more about how the brain works, and we're incorporating those insights into our AI models. It's a slow process, but I think we're on the right track. Maybe AGI is closer than we think.
I'm still skeptical. I think we're underestimating the complexity of intelligence. It's not just about processing data. It's about understanding the world, about having common sense, about being able to reason and plan. And I don't think we're anywhere close to achieving that with current AI technology.
I agree that we have a long way to go, but I'm optimistic that we can get there. I think the key is to focus on the fundamental problems, on representing knowledge and reasoning about the world. And I think that a focus on spatiotemporal reasoning is crucial.
Well, this has been a fascinating discussion. It's clear that there are many different perspectives on the path to AGI, and that there's no easy answer. But I think that by exploring these different approaches, by learning from the brain, and by focusing on the fundamental problems, we can make real progress. Thanks for joining us on Cognitive Spirals.